Section 3.5, exponential and logarithmic functions. For this section, we are just going to look at some of the even problem, numbered problems from each of the two parts, A and B, to 3, 5 together. Then you'll have the odds to do for homework. So open up your books to page 232. Problem 8, directions here say, complete the table for a savings account in which interest is compounded continuously. So we should know right away, since our interest is going to be compounded continuously, which formula we are going to use. Of the two interest formulas, A equals P times E to the RT. Problem 8, we are given the principal amount invested is $2,000. We are given the annual rate of percent, which is 1.5%. We are asked to find the amount of time it takes for this amount of money to double and the amount in the account after 10 years. So we have two different things that we are finding here. Let's first find the amount after 10 years. So plug in what we know. We're looking for A, that's the amount after 10 years. Principal amount invested was $2,000. The interest rate we're told is 1.5%. Don't forget to change the decimal, or I'm sorry, the percent to a decimal before you calculate with it. And the time, we want to know the amount in the account after 10 years. So from here, go to the calculator, plug that in. We get 2,000 times E to the 0.015 times 10 power. Hit enter. There's our dollar amount. Remember, this is dollars, so we should be rounding to two decimal places, so $2,323.67. There's the amount in the account after 10 years. Second thing we're asked to find is how long will it take the amount of money in this account to double? If I solve this equation for the exponential, we get A over P equals E to the RT. What we're solving for here is time, because we want to know the time to double, so I'm solving for T. This ratio of A over P, even if we are not given an original amount in the account, if the amount in the account is going to double, this ratio of A over P, the amount in the account compared to what we initially put in, will always be equal to 2. So keep that in mind. You don't have to be given an initial or principal amount invested. Okay, you could also be asked the question, how long will it take the account to triple in time? Well, then the amount in the account up here is going to be 3 times the principal amount, so that ratio will be 3. When we look at half-life problems later on, this ratio is going to be 1/2 and so on. So you don't necessarily have to be given original amounts. If you know that it's going to double, or it's going to be half the original amount, or it's going to triple and so on, we know what this ratio is. So now the only thing we need to know to solve for T is our interest rate. We know our interest rate is still 1.5%, and now we can solve this equation for T. Exponential equation. Follow your steps for solving. We want to isolate the exponential. In this case, the exponential is all by itself. So we moved right to the next step of taking the natural log of both sides. When I take the natural log of E, remember that cancels. I'm just left with 0.015 T. T is going to be the natural log of 2 divided by 0.015. Plug that into your calculator. We get 46.2098, round to 3 decimal points. That's going to be 46.21 years. So at an interest rate of 1.5%, it's going to take over 46 years for an initial deposit to double in size. Skip to number 10. This time in 10, we again know the initial amount or the principal investment. This time we know the time to double is 12 years. We want to find the percent rate and how much is in the account after 10 years. We're using our same formula here, A equals P times e to the RT. We know that our ratio of A over P, if it's going to double, is going to be equal to 2. We don't know the rate. That's one thing we're trying to find, but we're told that it takes 12 years for it to double. So we're solving this exponential equation this time for R. Once again, we're going to take the natural log of both sides. Natural log of 2 divided by 12. Plug that into your calculator. Natural log of 2 divided by 12. We get 0.0578. Round and change to a percent. That's going to be 5.778%. There's our percent rate. Next, we need to find how much will be in this account after 10 years. So we're initially investing $1,000. So we go back to our original formula, plug in what we know. We're looking for A, the amount after 10 years. The principal amount we're told is $1,000 that we're invested. We now know our interest rate from down here. It's 0.0578, and we are looking for how much is in this account after 10 years. Plug that whole expression into your calculator. 1,000 times e to the 0.0578 times 10 power, and we get $1,782.47. Skip to number 12. Problem 12 says that we're investing $300. We know the amount after 10 years is $385.21. Once again, just like the previous one, we first need to figure out what is that rate going to be. So let's plug in what we know here into our original equation. Again, we're starting with A equals P times e to the RT. We do know the amount at a certain time. There are $385.21. Principal amount invested was $300. We do not know the rate, but we know there were $385.21 after 10 years. So now from here, we're going to go ahead and isolate the exponential. So I have 385.21 over 300 equals e to the 10r. Exponential is isolated, so we take the natural log of both sides. Our rate is going to be the natural log of $385.21 over 300, all divided by 10. We're going to plug that whole expression into our calculator. Natural log of 385.21 divided by 300 divided by 10. There's our rate. We can see that that's going to be 2.5% when we change to a percent. Now that we know the rate, we can find the time to double. Again, we start with our original equation. Solve for the exponential. Again, that ratio of A over P, if it's going to double in size, is going to be that. We now know our rate is 2.5%, or 0.025. and we can solve for t. Plug that expression into your calculator, natural log of 2, divided by 0.025. It's going to take 27.726 years for this account to double. Skip down now to problem 20. Problem 20 says, complete the table for the radioactive isotope. We know that this radium has a half-life of 1,599 years. We do not know the initial amount present, but we do know that there are 1.5 grams left after 1,000 years. Okay, the formula we have just been using for our exponential growth was A equals P times e to the RT. For these half-life problems, the formula that you're going to use is Y equals C times e to the KT. Different variables, same exact formula. Okay, in our interest formula, A was the amount at a certain time. Y is going to be the amount at a certain time. P is the principal amount invested. C is the initial amount. T is still the time in years, so that's the same in both. And now our R for interest formulas was our interest rate. Our K value in this formula is going to be our constant that links our variables Y and C, sometimes called the constant of variation. So in this case, just like our interest formulas, we can't really calculate anything until we know the interest rate. In these problems, you cannot calculate anything until you know this value of K. So in a lot of these formulas that you're going to be using throughout this section, sometimes you'll just be given a formula. It's not going to tell you to do this, but you need to understand that you always must know what K is before you can do anything else. So they can give you a nice formula, give you a couple different situations in which you can use the formula, but if you don't know that value of K, you cannot do anything with the formula. So in this case, if I solve for the exponential, Y over C equals e to the KT, if we're talking about a half-life, that means that this amount at a certain time is half of this C amount. So let's say that our initial amount C was 10. That means Y is now going to be 5, but it doesn't matter. That what matters is that ratio is always going to be 1/2. And that half-life in this case occurred after 1,599 years. Exponential is isolated, so we take the natural log of both sides. K is going to be the natural log of 1/2 over 1599. Plug that into your calculator. Natural log of 0.5 divided by 1599. We get that value. Notice this is negative. Why is that value negative? Our interest rate for all the problems we did was always positive. Well, the reason the rate was positive is because the amount in the account was growing over time. In this case, the amount of this radioactive element is decaying or losing mass over time. So in this case, don't forget this e to the -4 here at the end. Okay, that means that that is 10 to the -4, so I need to take this decimal point and move it 1, 2, 3, 4 spots to get our K value. When you do that, let's get used to rounding to 3 non-zero digits. So when I do this, this is going to be -0.000433. So the first 3 non-zero digits behind the decimal point is what we're going to round to here. So our K value is going to be -0.000433. Now that we know K, now we can go and find anything else that we want to about this element. Go back to your original formula. y equals c times e to the kt. We're looking for the amount, or I'm sorry, the initial amount. We know the amount after 1,000 years was 1.5 grams. So we have 1.5 is the amount at a certain time. We do not know the initial amount. That's what we're looking for. We know our K value is negative 0.000433. And we know that this 1.5 grams is after 1,000 years. Solve this equation for C. C is going to equal, if I divide off the rest of what's over with C, we get 1.5 divided by e to the negative 0.000433 times 1,000 power. Plug this whole thing into the calculator. 1.5 divided by e to the negative 0.000433 times 1,000 power. And we see that we started with about 2.313 grams. Okay, last one we're going to look at in the first half here, skip down to problem 22. This time our half-life is 24,100 years. So we're again going to start with our initial formula, y equals c times e to the kt. We know this ratio of y over c, if we're talking about a half-life, has to be 1/2. When does that occur? After 24,100 years. Solve for k. Take the natural log of both sides, since the exponential is by itself already. Divide. K is going to equal the natural log of 1/2 over 24,100. Natural log of 1/2 divided by 24,100. 10 to the negative fifth now, so I need to add 4 zeros out front. Negative 0.0000288. There's our constant of variation. Again, it is negative because the amount of this element is decreasing over time. Go back to your original formula, y equals c times e to the kt. Plug in what we know. We know after 1,000 years there are 0.4 grams left. We don't know the initial amount. We know our constant, we just found that, negative 0.0000288, and we know that there was 0.4 grams after 1,000 years. Solve again for C. Divide by what's attached to C on the right side. And plug that whole expression again into your calculator. 0.4 divided by e to the negative 0.0000288 times 1,000 power. We see that we started with 0.412 grams.